Earlier we have discussed the questions that can be asked from module 1 and 2. Now here is time for module 4. Let me read the question. A steel rod, the ultimate stress is given. Ultimate stress is nothing but the maximum shear stress a material can withstand before it fail or fracture is ultimate stress, that is 1089.5 megapascal. Now the yield stress is given 689.4 megapascal. Yield stress is the stress such which a material begin to undergo plastic deformation. After that stress, the material will go plastic deformation, that is it will not when the force is removed, it will not regain its original shape. And then the endurance stress is given. Endurance stress is the stress that a material can withstand due to infinite number of cyclic loading. And the stress is subjected to tensile load, which varies from 120 kilonewton to 40 kilonewton. That is the maximum force, and the minimum force is also given. Design the safe diameter of the rod using Soderberg equation. Adopt factor of safety as 2, stress concentration factor as unity, and correction factors for load, size and surface are 0.75, 0.85 and 0.91 respectively. These are all the given data. Ultimate stress 1089.5 megapascal. Megapascal is same as Newton per mm square, so we don't need to change the unit. Ultimate stress 689.4 megapascal. Endurance stress 427.6 megapascal. Maximum force 120 kilonewton and minimum force 40 kilonewton. And the correction factor for load 0.75, for size 0.85 and for surface 0.91. In the question it says that the tensile load is acting. We know that tensile load is an axial load, and we are supposed to design a diameter. So we have to find the diameter using Soderberg equation. The factor of safety is given as 2, and the stress concentration is unity. Therefore value of stress concentration is 1. The Soderberg equation is KTF sigma A divided by ABC sigma endurance plus sigma M by sigma YP is equal to 1 by N. We don't need to by heart this equation. It is available in the data book, page number 25. In the question it is says that a steel rod. Therefore for ductile material, that equation 2.21a, that equation we know the equation for sigma A and sigma M. Sigma A is equal to Fa by A, sigma M is equal to Fm by A. Fa is equal to F max minus F minimum by 2, which is equal to 120 minus 40 by 2, which is equal to 40 kilonewton. Fm is equal to F max plus F minimum by 2, which is equal to 120 plus 40 by 2, which is equal to 80 kilonewton. This equation also we don't have to by heart. This is available in the data book, page number 24. Below that equation 2.17a, we can see that this equation by substituting the value in the sigma A, 40 into 10 raised to 3 divided by pi by 4 d square. Sigma M is equal to 80 into 10 raised to 3 divided by pi by 4 into d square. We keep that d square as unknown. We know the equation for KTF. KTF is equal to 1 plus Q into KT minus 1. Q is the notch sensitivity factor and KTF is the stress concentration during fatigue. The value of KT is given as 1, so 1 minus 1 there becomes 0. 0 into Q, that all term becomes 0, and 1 plus 0, the value of KTF becomes as 1. We know the value of KTF. KTF is 1 into sigma A. Sigma A is 40 into 10 raised to 3 divided by pi by 4 d square divided by ABC. A is correction factor for load, that is 0.75, into B is correction factor for size, that is 0.85, into C is correction factor for surface, that is 0.91, into sigma endurance. It is given that 427.6 plus sigma M. Sigma M we have found out that sigma M 80 into 10 raised to 3 divided by pi by 4 d square divided by sigma YP. sigma yp is given as sigma yp is nothing but the yield stress, that is 689.4, that is given, is equal to 1 by n. 1 by n is that factor of safety, which is 2. By solving this, we get the value of d as 26.57 mm. We can round it up to the highest decimal, that is 27 or 28 mm.